Okay, today we're going to talk about the superfactor machines in data science course week 6. The learning outcomes is upon completion of this session, students are expected to be able to build predictive models using supervised and unsupervised learning. This is some common algorithm in machine learning. From this, last semester, we already discussed about the naive Bayes, decision trees, and deep learning also came in for the unsupervised learning. And also, I believe all of you already know about the linear regression because this is a very simple method. In terms of the power of expressions, the winner is deep learning because you can use deep learning to solve a very high dimensional data. But for the other aspect like ease of interpretations, ease of use, training speed, prediction speed, linear regression has the highest number. Yeah, this is the scale from 1 to 10. In today's session, we're going to focus on support vector machine because this is also a famous and well-known algorithm to solve the problem in classifications. So there is no single method work best for all cases. So it depends on your problem. Linear classifier cannot be used to fit simple nonlinear functions like exclusive OR. Okay, you already knows about this when we talk about the neural network last semesters. The simple neural network cannot solve this kind of problem when the data is not linearly separable like this. So we need something else. For example, we can use decision trees or nearest neighbor, or the third alternative is support vector machines. Okay. This is the history of SVM. SVM was first introduced in 1992 in this paper, a training algorithm for optimal margin classifiers, proposed by Bowser et al. So the simple explanation is like this. Suppose we want to classify two different classes of the data. So this one belong to class plus 1 and this one belong to class minus 1. Yeah, negative and positive. So we take an input x and then we fit into the function, into a functions, and then we map this x and then we predict the output y estimate. Okay, so if we see the data like this, we can simply draw a line between these two data because this is really clearly separable, right? But how about this one? Yes, this one also a good classifiers. This one? Okay, this one also good at classifiers. So we have so many alternatives to draw the classifiers. But which one is the best? Okay, this is the idea of support vector machine. It takes the margins, yeah, it maximizes the highest margin here, which can push the data away as far as possible. So the data point is called vector. The line here, the classifier itself, the line that separates the data between two classes called hyperplane, yeah, line. And then from this point to this point, yeah, this one is the margin. This is the simplest kind of linear supervector machine. What is actually a supervector? Supervector are those data points that the margin pushes up against. So something in the very edge, yeah, in the border. is called support vector, like this point, and this point. How about the nonlinear SVM? So how about if we have the data like XOR, which we cannot easily draw a line to separate between black and white, between positive and negative. One way to do that is to simply transform the data into higher degree of polynomial. Yeah, for example, we have one-dimensional data like this, red, this is positive, positive, and then negative in the middle, and then positive, positive. So how do we transform this data into higher dimensional space? This is one dimension and this 2 dimension. So one way to do this is apply a polynomial functions fx equal x squared to transform the data from one dimensional to 2 dimensional. So we added another dimension in here, which is a function from this to its square. So if you see at the point, this is the x is still the same, but we can move the y a bit higher, so we can draw the hyperplane in here. That's the idea. How about higher and higher dimensional space? For example, we have 2 dimension. We want to go up higher, so we can linearly separate the data like this. So the idea is the same. We just need to map the data from this is the symbol for the 2-dimensional space to 3-dimensional space. So instead of using x1, x2, we have z1, z2, and z3. This is the visualization of polynomial degree. And how about the kernel trick? Yeah, this is also common in SVM. This is one feature that we can use in SVM. The problem when we transform the data to higher dimensional space, the higher the dimension, the higher the computational complexity. So in here, the researcher present what we call kernel trick. A kernel trick, especially for the higher dimensional space, is to help to transform this kind of data into this kind of data and even higher. So when we cut this hyperplane, it looks like this in the original dimension. How many type of kernel function that we can use? It's quite a lot, yeah. The most common one is polynomial function, Gaussian, sigmoid, linear kernel functions, hyperbolic tangent, graph, string, and tree kernel functions. So this is the visualization. It looks like this. The linear is like this, just linear without any degree. Second polynomial looks like this. You can separate the data like this. Third polynomial, you can even draw another curve, yeah. And radial, you can draw the hyperplane like this. You cut in the radial basis. And then sigmoid, you can draw 2 lines in your original space. So actually kernel function is a shortcut to avoid complex calculations. So this is the software that you can use, all these of SVM implementations. The most common one is libsvm. Okay, and this is the reference. Thank you.